In previous examples, we've looked at the relationship between the Gini index and violent crime rates. What we're going to do in this example is try and prove that yes, in fact, there is a linear association, that is, they are linearly independent, or kind of fall off and say, you know what, maybe they're actually independent, maybe there's no association, at least as far as we can prove. Now to do this, we're going to be running a hypothesis test because there's something I want to prove, and it's a hypothesis test on the slope because I want to show a linear association. Knowing this, I go ahead and I write out my first step. My first step is always to list. I list B1, which is my slope, 178.08. I'm going to list N as well, which is 452. Degrees of freedom, because I'll be using a t-table, is 450. I need SE as well. At this point, I need to go ahead and write down my hypothesis. My hypothesis has two parts, H0, what I assume, and HA, what I'm trying to prove. Now, in previous types of hypotheses tests, we've done things like P equals or mu equals when we're dealing with proportions or averages. Here, I'm doing a slope test, which means I need to make an assumption about what B is, but not just what B1 is, that's a sample statistic, what the slope would be if I took the entire population into account. So rather than use B1, we use beta 1. Beta 1 is the slope of the population regression equation. Now, as we talked about in the introduction here, I'm going to assume beta 1 equals 0. When I make that assumption, it's assuming that the slope is 0, which means I have no linear association going on. That's not what I'm trying to prove, however. I'm trying to prove there is a linear association, that is, they're linearly dependent, which means I'm trying to prove that beta 1 is not equal to 0. There's something going on. The slope is not equal to 0. Step 3 is my calculations. When I do my calculations, I need to normally calculate SE first. Once again, we're not doing that by hand, so we'll just go ahead and list it here, 157.04. And then we also need to list my t-score. My t-score is always my actual minus my expected divided by my standard deviation estimate. In this case, my actual is 178.08. My assumed value right here is 0. And I divide it by my SE, which is 157.04. Notice that subtracting off 0 doesn't actually change anything, so I could just leave that off if I wanted. Which gives me 1.33. After I've gone this, the next step is to go ahead and go on to my p-value. To find my p-value, I'm going to have to use my t-score of 1.33 and my degrees of freedom in combination on the t-table. Now with degrees of freedom 450, it's not actually on the table, so I round down. I'm going to be using degrees of freedom 100 then, looking across here. I'm looking for a t-score of 1.33, which would be right here in the center, in between these two. Knowing that, I trace both of those two up to the top, here and here. What this tells me then is that my p-value is in between those two end tails, which are 0.1 and 0.05. Now there's one thing I have to be cautious of, and that is this is a two-sided hypothesis test. I can tell it's a two-end tail or two-sided because my alternative hypothesis is not equal to. Because it's two-sided, it's not actually good enough to have this. I need to double these two values. So I'll double that and double that. This will give me 0.2 and 0.1, meaning my p-value is between 20% and 10%. I put in my greater than symbols because on the top of that t-table it always goes bigger to smaller, and because 20% is bigger than 10%. Now I've got all this information down, the final step is to go ahead and write my conclusion. To reach my conclusion, I compare my p-value to my significance level, 0.05. In this case, my p-value is between 20 and 10%, so it's definitely bigger than 5%, which is kind of disappointing, because if my p-value is bigger than 0.05, that means I'm going to fail to reject H0. What it means when I fail to reject H0 in this case is, as always, I don't have enough evidence, but specifically here, I don't have enough evidence to show that there's a linear association. That is, I can't prove they're linearly dependent, which means for all we know, they might actually be independent. That is, there may be no relationship between the Gini index and violent crime rates in cities in the United States.